This is problem 1333 on page 826. An uncontrolled automobile traveling at 65 miles per hour strikes squarely a highway crash cushion of the type shown, in which the automobile is brought to rest by successively crushing steel barrels. The magnitude F of the force required to crush the barrels is shown as a function of the distance x the automobile has moved into the cushion. Knowing that the weight of the automobile is 2,250 pounds and neglecting the effect of friction, determine A, the distance the automobile will move into the cushion before it comes to rest, B, the maximum deceleration of the automobile. All right, so again, let's set up our, well, I guess I could draw it at the board quickly. So basically, here's our car. It's about to crash. It was an ugly car anyway. Crash into a whole bunch of barrels. Just a bunch of barrels stacked up. They're all sitting with, open at the top on just ground. And there's a hard stop back here. It's not going to move. They've given us a coordinate system. Y in this direction, Z coming out of the board, and X in that direction. But they've also given us a graph to show us how the force in thousands of pounds, kips in other words, varies versus position. So let me align this, a little bit better. There we go. So the force that the barrels apply in thousands of pounds versus position x of compression, which is measured in feet. Well, I'm not sure that that's at the end, but in any case, we've got 18,000 pounds for the first 5 feet, 27,000 pounds for the next 9 feet, so up to 14 foot. That's 27. And then finally we've got 36,000 pounds from there on. Okay. All right, the automobile is 2,250 pounds mass and is traveling 65 miles an hour. I think the first thing we should do is to calculate the speed of the automobile in feet per second. So let's multiply this by 5,280 feet per mile and 1 hour per 3,600 seconds. What do we get when we form that computation?
95.3.
Thank you, 95.3 feet per second. Now, what's going to happen is these barrels are going to apply a force in this direction, but the motion's in that direction. So are the barrels adding to or removing energy from the car? If I'm in that car, I hope they're removing. If I'm in that car, I hope I'm not texting and driving, right? But anyway, hopefully my excuse is that the brakes quit, so we're gone. So if you think about it, what does the area under this curve represent? It represents work done by the barrels on the car, doesn't it? As a matter of fact, 18,000 pounds times 5 feet, well, multiply 18,000 by 5, what do we get?
90.
So that's 90,000 foot-pounds force of work that's done in 5 feet, right? That's how much work the barrels can do on the car. How much energy does the car have? Well, T1 plus U, 1 to 2, T2. Well, the car is going to come to rest at the end, at least I hope so, before it hits the concrete. So we're going to have 1/2 mv1 squared plus the work done. Well, that work done is simply going to be force times distance. Now, we've got to be careful. I'm going to put a summation here. Not because there are multiple forces doing distance, but there's going to be force at different levels doing work for some distance. Does that make sense? This must come out to 0. So 1/2 m, but let's be careful because really this should be a dot product because the force is acting in one direction, the distance is the other, so I probably should have put a minus sign there. So if we rearrange this just a little bit, we'd get sum of force times distance on the other. Let me expand that just a bit and say F1 D1 plus F2 D2 plus possibly F3 D3. I don't know that that much will be required, but what I'm saying is that there's going to be some distance moved through these various forces. I don't know how much they will be. We'll find out as we go. Okay. So let's figure out how much energy the car has in it. The mass of the car is 2250 pounds mass. It's moving at 95.3 feet per second. That has to be squared. So notice what we'll have from this is pounds mass feet per second squared times feet. So this is a force times the distance, isn't it? But it's not a pounds force times a foot, right? What do we need to multiply by in order to convert those pounds mass feet per second squared into pounds force? What do we do?
Divide it by 32.2.
32.2 what?
Pounds mass feet per second squared.
Right. And that would be 1 pound force, isn't it? Okay. So this will give us foot pounds force or pounds force feet, which is what I prefer for energy. So what number do we get here? How much energy are we talking about?
317,309.
5 foot of barrels is gone. You only get 90,000 foot-pounds of work done by those barrels. We zip through that. How much energy are we talking about for the next segment? Well, that would be 5 from 14, 9 feet. So basically what I'm saying here is that D1 is 5 foot, D2 at most is 9 foot, right? So the amount of energy here would be 27,000 pounds times 9 foot. What is 9 times 27,000? Do we have that?
243,000.
243,000. So if we take that, looks like it's going to stop in here somewhere, isn't it? Because 243,000 plus 90,000, we're looking at 333,000 foot-pounds. We won't need to get into this section, okay? So I don't actually need that. But we get all of this, which is 90,000 foot-pounds, or I prefer pounds feet. Take it away from 317,000, so let's just do it this way. Let's just take this to the other side of the equation. So we'll write 1/2 mv1 squared minus F1 D1 equals F2 D2. So over here we already know what that is. It's 317,309 less F1 D1, 90,000 equals F2 D2. Make that look more like a 2. So on this side we have what? 227,309 equals F2 D2. I did the math right in my head. Yeah, I think that's right. You take away 100,000, add back in 10. Okay. So D2 must be simply 227,309 over F2. Now let's be careful. These are pounds force feet, and F2 is pounds force. In fact, F2 is 27,000 pounds force. So that's how many feet into the second section of barrels the car ends up going. So I need 227,309 divided by 27,000. What do we have for that?
8.42.
8.42. So what that means is the car will travel in a distance of 8.42 plus 5. 5 and 8 are 13, so 13.42 feet. That's how far into the barrels the car is going to go. Okay. Well, not too bad. Just a graphic problem. The distance the automobile will move into the cushion before it comes to rest. That was part A. Part B, the maximum deceleration of the automobile. Well, force is just mass times acceleration, isn't it? So the more force applied to the car, the higher the acceleration or deceleration will be. We don't get into this section, we only get into this section, so the maximum force applied is 27,000 pounds. So basically the deceleration is going to be force over mass, which is going to be 27,000 pounds force divided by the mass of 2250 pounds mass. Why would we care about the maximum deceleration? Because if you get too much deceleration, you're going to kill the occupants. Right? Not a good idea. But these are not units of acceleration we are used to. How can we get this to feet per second squared? Pound force per pound mass is acceleration. If we had feet per second squared, we could compare that to G's, couldn't we? By the way, pound force per pound mass, already G's, but let me show you. So there's 32.2 feet per second squared pounds mass, if you want to write it that way, for every pound of force. That'll take care of the pound force, pound mass. But there are also, well, let's see, 1 G for every 32.2 feet per second squared. So we've already got G's. So take 27,000, divide it by 2250. What do we get?
0.1188.
How much?
0.1188.
You get 12.
Oh,
Yeah.
I'm doing something wrong with it.
It's more than 10. How much
It's
is
12.
12. So the occupants of the car are going to experience 12 G's. Will they die? I don't know. I don't know how much an untrained human who's just looked up from their cell phone will manage to pull.
They're asleep. And then they're nice and younger.
They'll be asleep by the time they stop. Maybe so. They might black out. Let's see. Something. Oh, did you know that hard drives, at least mechanical hard drives, which are becoming more rare, have certain maximum G ratings, so you can drop them. And if you drop a hard drive on a hard enough surface where it stops with much higher deceleration, you can damage it. Fortunately, most hard drives are switching over to solid state, but you still can only apply so many G's to things before they just fall apart. Any questions about this problem? All right. I guess, oh, did you know there are also G-rated stickers? So basically where you put these stickers on the side of packages that you send, if your machinery can't decelerate too fast, you put these stickers on and it's a color indication. So if the package ever experiences an acceleration larger than, a certain level, it'll break a vial or something. You'll see that, the package was mishandled.